Welcome back to the Deep Dive, where we plunge into ideas that genuinely reshape how we see the world. Today, we're tackling something that might just shake the foundations of how you think about science, reality, and, well, even truth itself. For centuries, brilliant minds think Galileo, who famously said, "The book of nature is written in the language of mathematics," or Eugene Wigner talking about the unreasonable effectiveness of mathematics. They deeply believe that math isn't just a tool we use, it's the actual language of the universe. The essential key, the cosmic blueprint.
And that's a really powerful idea, isn't it? It's deeply ingrained. It shapes so much of how we approach science.
Yeah.
But what if we've been looking at it just a little bit sideways? What if reality doesn't actually do math?
Yeah.
Not in the way we've thought. Now, don't get me wrong. Our mathematical models are incredibly powerful, amazing tools for approximation, for prediction. They help us navigate the world, understand things, even change things. But this deep dive, we're going to explore a, let's say, provocative idea. What if these models, these equations, aren't the ultimate explanation? What if they're more like our human design maps of a territory that exists completely independently of us?
All right, that's the core challenge we're wrestling with today. It's fascinating. So our mission here is to really dig into this concept. We'll look at the independence of reality from our math, that crucial difference between just predicting something and truly explaining why it happens. And we'll even touch on some cutting-edge alternatives like neural networks. We're hoping to uncover some insights that might shift how you think about science itself, what it is. So yeah, buckle up. Let's dive in. Okay, so let's start with this bold premise. It kind of goes against the grain. The sources we've looked at suggest pretty strongly that reality existed for billions of years before humans even came up with the number one, let alone calculus. And the universe will keep doing its thing, even if we all collectively forget algebra tomorrow. What's the gut argument for this independence of reality?
Well, the core idea, and it's quite profound when you really sit with it, is that it reframes what we think scientific truth is. Maybe it's not about discovering some pre-written cosmic laws etched in stone or, math. Maybe it's more about us, humans, inventing increasingly useful maps. We're not reading nature's instruction manual. We're making the best navigation tools we can. Think about it.
No.
The physical universe, it was doing its thing for, 13.8 billion years before we even had a concept of geometry. Stars burned, galaxies spun, gravity worked, chemicals reacted, all without needing a human equation to describe it.
Okay, yeah, when you put it like that.
So the fundamental principle is just that. Reality operates on its own terms, completely independent of our mathematical descriptions, our equations. They're sophisticated, yes, brilliant representations, incredibly useful approximations, but they aren't reality itself. They are the tools we use, the language we created to try and understand and interact with reality, but they aren't the thing itself.
Right. So if reality was doing its thing long before us, and our equations are just our way of describing it, then even our biggest scientific wins, our most solid laws, must fit this idea too. Like, take Newton's laws of motion. They're everywhere, right? Building bridges, sending probes to Mars. They feel so fundamental, so true. But the sources we're drawing on say, provocatively, they're just approximations. How can something that useful be just approximate?
That's a really great question because Newton's laws are incredibly effective, absolutely brilliant within their specific domain. They give excellent approximations for objects we can see, moving at speeds we typically encounter in everyday life, calculating a baseball's path, designing a car. They work fantastically well.
Yeah.
But the key word there is domain. They have limits, push things really fast, like close to the speed of light, and they break down. They don't give the right answers anymore. That's where we need Einstein's relativity. His equations are a better map for that territory.
Okay, so it's about the context.
Exactly. And then you go really small down to the subatomic level, and Newton is completely out the window. You need the weird probabilistic rules of quantum mechanics. It's a whole different map for that tiny scale. But this doesn't make Newton's laws wrong in their own domain. It just highlights their boundaries. Think of it like having a really accurate street map of London. It's fantastic for getting around London. But try using that London map to navigate Tokyo. It's useless, right?
Wrong tool for the job.
Precisely. So scientific progress, viewed this way, isn't necessarily about finding the one final ultimate equation for everything. It's often about realizing the limits of our current maps, our current models, and then developing new, more comprehensive maps that cover more territory or describe the existing territory more accurately.
Okay, that makes sense. So we've got these models, these brilliant approximations like Newton's laws, but they have limits. So that brings up a really key question about what we're actually using them for. Are we trying to understand the absolute deepest why of things? Or are we mainly focused on, well, predicting what happens next. The article really hammers on this distinction, prediction versus explanation. It sounds like knowing what will happen is different from knowing why.
Yes, that's a really critical distinction, especially from a practical scientific standpoint. The primary job of these mathematical models in science, empirically speaking, is prediction. We test them based on their usefulness. How accurately can they forecast what a system will do? Can this weather model predict the hurricane's path accurately enough to save lives? Can our orbital mechanics equations get the Mars rover to land in the right spot? These are measurable things, objective tests of a model's success. And they provide incredible value, right? This does-it-work approach is, well, it's the bedrock of a lot of science.
Yeah, you can't argue with results. If it predicts accurately, it's useful.
Exactly. If a model tells us what's coming, that's hugely valuable. Sometimes, even if we don't fully grasp all the underlying deep down causes in the most fundamental way.
I can definitely see the power there,
Yeah.
focusing on prediction and practical results. It's undeniably useful, but there's that nagging feeling, isn't there? That desire for the why. If we sort of sideline true explanation, do we risk ending up with a very clever but maybe superficial understanding? We know what happens, but not really how or why it connects at the deepest level.
That's the tension, absolutely. You've nailed a core point in the philosophy of science. True explanation, like really true explanation, means understanding the causal links, the cause and effect relationships at the most fundamental level. Often that means diving down into the quantum scale where individual particle interactions happen. Imagine trying to explain a traffic jam by tracking every single electron in every car's battery.
Yeah.
It's that level of complexity, fundamentally.
Okay, that's impossible.
Well, practically speaking, yes. The things we usually want to explain, a hurricane, a disease spreading, an ecosystem changing, these are macroscopic phenomena. They emerge from countless, mind-bogglingly complex interactions happening at that micro level. So this creates a huge challenge for us, an epistemological challenge, basically, a problem with how we can even know things. Because those fundamental causal steps, the real why down at the bottom, are often completely inaccessible. We can't directly see or measure them all. And then you throw in quantum mechanics itself, with its built-in uncertainty and probabilities. It messes with our simple classical ideas of cause and effect anyway. It suggests that maybe the why isn't even a neat chain reaction, but more like a web of likelihoods. So yes, we crave the why, but getting to it, fundamentally, that's incredibly hard, maybe even impossible with the tools we have.
Okay, so given these challenges, especially for really complex systems where those neat, elegant equations just don't seem to cut it, and the fundamental why feels miles away, what else are scientists using? It sounds like we need more than just traditional math formulas in the toolbox.
Absolutely. And that's where things get really interesting right now. We're seeing a major shift, or maybe an expansion of the toolkit. One of the most promising alternatives, which is getting a ton of attention, is using neural networks, machine learning systems. These systems can be incredibly good at approximating complex functions, finding patterns in data that are just too messy or complicated for a human to easily write down as an equation. They're particularly useful for systems where things are highly nonlinear or there are just tons of interacting variables.
Right, so unlike our traditional approach where we, the scientists, have to figure out the formula first, like FMA or eMAMC,
Right.
these neural networks, they work differently. They don't need us to tell them the exact relationship between X and Y beforehand. They can handle massive amounts of data, weird nonlinear connections. They adapt. It's almost like they discover the patterns for us.
That's a great way to put it. They essentially learn by example. You don't program them with explicit rules like if this, then that. Instead, you feed them huge amounts of data related to the problem, and the network adjusts its internal connections, millions, sometimes billions of them, to figure out the patterns linking the inputs to the outputs. This lets them capture really subtle relationships, emergent behaviors in complex systems, without us having to explicitly model every single interaction. Think about image recognition or complex climate modeling, or even trying to predict stock market fluctuations.
Things with just tons of factors.
Exactly. Systems with so many moving parts, so much feedback and nonlinearity that writing a clean equation is just not feasible. Neural networks can find predictive power there. They learn the complex mapping from inputs to outputs directly from the data. So they let us make progress, achieve practical goals, even when that fundamental why is still kind of murky. It's a powerful trade-off.
That sounds incredibly powerful, almost too easy.
Ah.
I mean, there has to be a catch, right?
Yeah.
If they're so good at prediction, what are the downsides? Especially if we still care at some level about that deeper why.
Oh, there are definitely significant limitations, big ones. While they can be amazing predictors, their inner workings are often, as people say, a black box.
Mm,
Imagine you have this amazing chef,
right.
consistently makes incredible food. You give them ingredients, you get fantastic dishes back. You can predict the quality, but you have absolutely no idea what goes on in the kitchen. You don't see the recipes, the techniques, why they chose that spice.
So you get the result, but not the process.
Exactly. You know what prediction it makes, often very accurately, but you don't necessarily understand how it arrived at that prediction or why those specific connections were learned. So they satisfy the prediction need, but they don't automatically give us that deeper causal understanding. We get the what, but lose the how and why, and that can be a real issue in fields where you need transparency or accountability. Think about using AI in medical diagnosis or, say, loan applications.
Yeah, you need to know why it made that decision.
Precisely. Plus, they need enormous amounts of good training data. Garbage in, garbage out still applies. And they can be brittle. They might be great within the range of data they were trained on, but face them with something truly new outside their experience, they can fail, sometimes spectacularly. They don't reason from first principles like a human ideally would.
Okay, this is genuinely making me rethink things. So if reality doesn't really do math like we thought, and if our best tools, whether they're equations or these neural nets, are fundamentally approximations geared towards prediction, what does this mean for how science actually gets done? How should scientists approach their work? Does it mean we just give up on finding elegant equations?
No, not at all. It's not about abandoning equations. They're still incredibly powerful and insightful where they work. What this perspective really encourages is, let's call it methodological flexibility or pluralism. It suggests scientists shouldn't be dogmatically attached to just one type of tool or one philosophical ideal. Instead, use whatever works best for the specific problem at hand. Maybe that's a traditional equation. Maybe it's a massive computer simulation. Maybe it's a neural network. Maybe it's something totally new we haven't invented yet. The measure of success becomes, practical effectiveness. Does it help us predict? Does it help us solve the problem? Does it lead to tangible results? It's less about adhering strictly to one mathematical framework or chasing the ultimate explanation, and more about choosing the right tool for the job and being really honest about what that tool can actually do and what it can't.
But doesn't this raise a kind of almost existential question for science? If all our models, even the best ones, are just approximations, if there isn't necessarily one ultimate mathematical truth out there waiting to be discovered, does that somehow diminish scientific knowledge? Does it make our breakthroughs seem less real or less valuable? It feels like it could undermine the certainty we often associate with science.
That's a really profound question, and I think the answer is actually no, it doesn't diminish it. In fact, it might make it stronger in a way. What it encourages is a healthy, appropriate humility. Our scientific theories are the best approximations we have right now. They're incredibly powerful, refined through rigorous testing, but they are always provisional. They're not the final, absolute, unchanging word. And that understanding is actually what drives science forward, isn't it? It fosters continuous questioning, always pushing the boundaries, looking for where our current models fail, and it keeps us open to completely new ways of thinking, to paradigm shifts when the old maps just aren't good enough anymore.
So it's about progress, not finality.
Exactly. And philosophically, it's huge. It suggests maybe mathematical objects, numbers, shapes, equations, aren't things that exist out there independently like Platonic forms. Maybe they are powerful conceptual tools we invented, human constructions for recognizing and describing patterns, incredibly effective tools, but are tools. Science then becomes this ongoing process. We're continually developing better and better approximations, more useful maps of reality. It's not a quest for some single, ultimate, complete truth that will someday be finished. Our approximations can be objectively better or worse, right? We measure progress by how well they predict, how useful they are, how wide a range of phenomena they can cover. That makes science robust, adaptable, always evolving. That's its real strength.
Wow. Okay. So we've taken quite a journey today, a deep dive into this really thought-provoking idea that reality fundamentally just is, independent of our descriptions. And our models, whether they're elegant equations or complex AI like neural networks, are these incredibly powerful approximations. Their main strength lies in prediction, helping us navigate and interact with the world. But maybe they don't always give us that ultimate fundamental why and the future of science. It sounds like it might involve embracing a much wider toolkit, being more flexible, and maybe a bit more humble in our approach.
I think that's a great summary. The ultimate lesson, maybe, is simple but quite profound. Reality doesn't really care about our math or our understanding. It just operates. Our entire scientific enterprise, all our theories and models and experiments, it's our ongoing, very human attempt to create useful approximations of that independent reality. And success isn't measured by finding some final absolute truth, but by practical effectiveness. How well do our maps help us navigate the territory? How useful are they? It's about having a useful, evolving conversation with the universe, not about receiving some final dictation written in the language of mathematics.
So here's something to leave you with, something to mull over. If even our best scientific models are inherently provisional, limited approximations, constantly being refined, sometimes replaced, what does that mean for how you think about absolute certainty when you hear a scientific claim? Does it change anything? And maybe, just maybe, how might this shift in perspective from seeking ultimate truth to developing increasingly useful approximations? How might that change the way you approach solving problems, making decisions, or even just understanding the complex world around you in your own life? Lots to think about. We'll see you next time on The Deep Dive.